This video will illustrate the answers to AP Chemistry 1982 question D. We'll begin with part A, drawing the electron dot structures of the carbonate anion, carbon dioxide, and carbon monoxide. We'll begin with the carbonate anion. First, we need to determine how many electrons we would expect in our diagram. Carbon gives us 4 electrons, each oxygen gives us 6, and the -2 charge gives us an extra 2, a total of 24 electrons in our diagram. We'll begin by drawing the central carbon atom surrounded by 3 oxygen atoms. We decide to doubly bond one of the oxygens and singly bond the other 2. The double bonded oxygen gets 2 pairs of valence electrons, where each singly bonded oxygen gets 3 pairs, so each oxygen has a valence shell of 8 electrons. Notice that the singly bonded oxygens have 7 electrons near them, whereas a normal oxygen atom would only have 6, meaning each singly bonded oxygen has a -1 charge for a net charge of -2 for the molecule. We'll then draw one of the resonance structures of the same molecule. This will be a structure that looks similar but has a double bond in a different place. We then draw in where the electrons would have to migrate to form our resonance structure. Note that we still have only 1 doubly bonded oxygen and 2 singly bonded ones, meaning the net charge for this molecule is also -2. Finally, we draw the third resonance structure, which looks similar to the other 2, but has the double bond in yet a different location. Once again, we draw in the arrows to show where the electrons would have to move to form our third structure. This third structure will also have a -2 charge. And here we have the complete diagram for the structure of the carbonate anion. We'll move on to drawing carbon dioxide. Once again, we'll begin by calculating the number of electrons, 4 for the carbon and 6 for each oxygen, giving us a total of 16 electrons in our diagram. We'll draw a carbon atom flanked by 2 oxygen atoms, each doubly bonded to the carbon. Each oxygen atom also gets 2 valence electrons. Notice that this is the only structure that satisfies the rule that carbon wants to make 4 bonds and oxygen wants to make 2 bonds. Also notice that both carbon and oxygen have 8 valence electrons, satisfying a second rule. Finally, we move on to the carbon monoxide molecule. Carbon gives us 4 electrons, oxygen 6 electrons, for a total of 10 valence electrons. We draw a carbon atom, an oxygen atom, and a triple bond in between, and add 2 valence electrons to both the carbon and the oxygen to get up to our total of 10 electrons. Note that this is the only structure which will give us both 10 electrons and an overall charge of 0. Carbon normally wants 4 electrons, but in this case it has 5, meaning it has a charge of -1, whereas oxygen normally wants 6 electrons, but in this case it only has 5, giving it a charge of +1. The -1 charge on the carbon and the +1 charge on the oxygen cancel out, meaning the molecule's overall net charge is 0. This is the only structure that accomplishes this. We move on to part B, determining which of the 3 species has the shortest C to O bond length. We determine that it is the carbon monoxide molecule because this molecule contains a triple bond, meaning it is a bond with more electrons. Those electrons will exert a stronger attractive force on the nuclei of the carbon and oxygen atoms, pulling those 2 bonding atoms closer together. We can illustrate this interaction through a molecular model. Here we have a single bond, like in the carbonate anion. Here, a double bond, like carbon dioxide. And finally, a triple bond, the shortest of the 3, like in the carbon monoxide molecule. You can see how visually the triple bond looks shorter than the double bond, which looks shorter than the single bond. Finally, we have part C, predicting the molecular shapes of the 3 species. We'll start with the carbonate anion, which is of a trigonal planar shape. The reason for this is that the carbonate anion is made up of 1 central atom with 3 bonded atoms and no lone pairs. That means that the 3 oxygen atoms can spread out evenly over a plane, and with no central pair to push them down, they'll lie flat, as you can see in our model. Up next, we have carbon dioxide. This will be of a linear shape. The molecule is made up of just 2 outer atoms bonded to 1 central atom, and since there are no lone pairs on the central carbon atom, there's nothing to prevent the 2 oxygen atoms from aligning linearly. Finally, we have carbon monoxide. This will also be a linear shape because 2 atoms can only arrange linearly.